In this video, we will discuss the addition rule and multiplication rule. A compound event is any event combining two or more simple events. For the addition rule, the probability of A or B is equal to the probability in a single trial that event A occurs or event B occurs or they both occur. In math in general, but particularly in statistics, the word or is the inclusive or, which means either one or the other or both. The intuitive addition rule: to find the probability of A or B, add the number of ways event A can occur and the number of ways event B can occur, but add in such a way that every outcome is counted only once. The probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. The formal addition rule is that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, where the probability of A and B denotes the probability that A and B both occur at the same time as an outcome in a trial of a procedure. One way to apply the addition rule is to add the probability of event A and the probability of event B, and if there is any overlap that causes double counting, compensate for it by subtracting the probability of outcomes that are included twice. This approach is reflected in the formal addition rule. For example, 555 subjects are given a drug test and results are shown in the table below. If one subject is randomly tested, what is the probability that the subject had a positive test result or uses drugs? So here we have four possibilities. 45 of the 555 subjects both used drugs and had a positive test result. 5 of them use drugs but have a negative test result. 25 do not use drugs and have a positive test result. And 480 do not use drugs and have a negative test result. It's easier to solve this problem with the data in table form, as we can easily see which data needs to be counted. The first row consists of subjects who use drugs, while the first column consists of subjects who tested positive. The overlapping data is those who both use drugs and tested positive. We count each of the three boxes once to get the total number of subjects who had a positive test result or used drugs. 45 plus 25 plus 5 equals 75. So the probability of a positive test result or that the subject uses drugs is 75 over 555, or 0.135. Events A and B are disjoint or mutually exclusive if they cannot occur at the same time. Disjoint events do not overlap. For example, events A and B are disjoint if event A is randomly selecting someone for a clinical trial who is male, and event B is randomly selecting someone for a clinical trial who is female. Events A and B are not disjoint if event A is randomly selecting someone taking a statistics course, and event B is randomly selecting someone who is female. They could, after all, be both. When A and B are disjoint, the probability of A and B is equal to 0, so the probability of A or B is equal to the probability of A plus the probability of B. As mentioned in the previous lesson, we are certain with probability 1 that either an event A will occur or it does not occur. So it follows that the probability of A or not A equals 1. Because both A and not A cannot occur simultaneously and thus are disjoint, we can use the addition rule to express this principle. The probability of A or not A is equal to the probability of A plus the probability of not A, which equals 1. The rules of complementary events say that the probability of A plus the probability of not A is equal to 1. The probability of not A is equal to 1 minus the probability of A, and the probability of A is equal to 1 minus the probability of not A. Based on a journal article, the probability of randomly selecting someone who has sleepwalked is 0.292. So the probability that somebody has sleepwalked is 0.292. If a person is randomly selected, find the probability of getting someone who has not sleepwalked. Using the rules of complementary events, we find that the probability has not sleepwalked is equal to 1 minus the probability of sleepwalked. So 1 minus 0.292 is 0.708. The probability of randomly selecting somebody who has not sleepwalked is 0.708. Notation for the multiplication rule. The probability of A and B is equal to the probability that event A occurs in a first trial and event B occurs in a second trial. The probability of B given A represents the probability of event B occurring after it is assumed that event A has already occurred. Note that we used the probability of A and B differently here than we did when we were discussing the addition rule. In the context of the multiplication rule, the probability of A and B assumes A and B happen in separate trials, while in the addition rule, the probability of A and B assumes the events occur in the same trial. The intuitive multiplication rule says to find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event B is found by assuming that event A has already occurred. The formal multiplication rule is the probability of A and B is equal to the probability of A times the probability of B given A. When applying the multiplication rule and considering whether the probability of event B must be adjusted to account for the previous occurrence of event A, we are focusing on whether events A and B are independent. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. If A and B are not independent, they are said to be dependent. Don't think that dependence of two events means that one is the direct cause of the other. Having a working light in your kitchen and having a working light in your bedroom are dependent events because they share the same power source. One of the lights may stop working for many reasons, but if one light is out, there is a higher probability that the other light will be out. For example, drug screening and the basic multiplication rule. Recall these results from our previous drug screening example, using only the results from subjects who use drugs. Positive test results, 45, negative test results, 5, total 50. If two of these 50 subjects are randomly selected with a replacement, find the probability that the first selected person had a positive test result and the second had a negative test result. Then repeat part A by assuming that the two subjects are selected without replacement. So now this is the example with replacement. The first selection with 45 positive test results among 50 total results, the probability of a positive test result is 45 out of 50. And the second selection with 5 negative results among 50 total results, the probability of a negative test result is 5 out of 50. Now we apply the multiplication rule. The probability that the first selection is positive and the second is negative is equal to 45 over 50 times 5 over 50, which is 0.900, or 9/100ths. When we say without replacement in a probability problem, it means that we are removing the subject selected in earlier trials from the population. For example, if we draw a card from a full deck of 52 cards, there are only 51 cards remaining in the deck. The removal of a subject from a population affects the probability of further trials. So, in this case, the first selection with 45 positive results among 50 total results, the probability of a positive test result is 45 out of 50. In the second selection, with 5 negative results among 49 total results, because we removed that first, result of the first selection, the probability of a negative test result is 5 out of 49. So the probability that the first selection will be positive and the second will be negative is 45 over 50 times 5 over 49, which is 0.0918, which is slightly higher than the probability we found in the first part of the example. We'll pause here, and I'll start the video with the next page.